Chapter 27, last chapter in the book. So we're still doing inference in this chapter, which means we're still dealing with confidence intervals, hypothesis tests, but this time we're doing them on regression equations. So this goes all the way back to Unit 2, where we were dealing with scatter plots, associations, R-square values, and all those. For the example in the notes, we have a scatter plot showing all 178 half marathon times for a professional runner. The explanatory variable is the temperature on race day, and the response variable is the time that it takes for the runner to run the race. Since this is all of the runner's times, this is the population of all of those data values, paired data values between the temperature and the time it takes to run this half marathon. We're going to sample 11 of these paired data values from the population of all 178. So first off, let's go through a refresher on regression. So here's our sample of 11 values from that scatter plot. Enter both those lists in your calculator, and then we want to run the regression using these directions. So if you're using the 84, we're going to do it with these directions. 89 is here. Okay, when we run the regression, it's going to give us an A, B, which are the y-intercept and the slope, and then R and R squared values. After you run the regression, make sure you view the scatter plot. Ideally, we want to do that first to make sure it's linear, and also view the residuals plot. Hopefully you know how to do that. If not, we'll go over that again in class. When we actually create the equation, it would look like this down here on the bottom. Remember, the y variable is predicted. That's why it has that hat on it. Okay, temperature is the explanatory variable. So when it comes to describing association, we use FUDs, which is form, unusual features, direction, and strength. And we would say something like, the association between the temperature on race day and the time it takes the runner to complete the half marathon is positive, linear, and strong, with no unusual features. We'd also want to make some general statement using that correlation coefficient of R equals 0.811, saying that generally speaking, as the temperature rises, the time to finish the race increases with it. A few more questions you should be familiar with regarding regression. When it comes to interpreting the slope, we always say something like this. For each increase in 1 degree of Fahrenheit, we expect the time to complete the marathon to increase by an average of 0.069 minutes. Okay, we're always talking about an increase in 1 in the temperature, and the explanatory variable is going up by an average of this amount. For interpreting the y-intercept, that's this value here. If the runner completed a marathon in 0-degree weather, we would expect it to take 139.5 minutes, or it would take an average of 139.5 minutes. The R-squared value, which is called the coefficient of determination, that's the sentence where we say 65.8% of the variation in the time required to complete the marathon can be explained by the temperature on race day. And then finding residual, let's say we looked at that data point, 46 degrees, 142.1 minutes. If we plugged 46 degrees into the equation, we get 142.7. Okay, observed minus expected gives us a residual of negative 0.6. So that was the quick 3-minute refresher on all of Unit 2. Now moving forward, we have this equation that's based on a sample of 11 values taken from the population of all 178 data points based on this runner's race times and the temperature on race day. If we were to take a different sample of 11 other races, we would get a different equation. It would have a different slope, it would have a different y-intercept, etc. So the values in our equation are statistics, and those are going to vary with every sample that we take. So that 0.069 would change, that 139.5 would change. But there is a true slope and a true y-intercept of the line through all of those points of the scatter plot that we saw on the second slide in these notes. All right, so when we're talking about these equations, we've been using this equation here, y hat equals b sub 0 plus b sub 1x. That's for a sample. But there's an equation for the population too. For populations, we use Greek parameters. It's really the same equation, It's just referencing population parameters. Okay, the fact that if we actually looked at every single one of these races, all right, there's a true slope that's represented by all of that data. So thinking a bit ahead here, what we're going to do is take our sample and use it to create a confidence interval for the true slope, or run a hypothesis test on it for the true slope. So just like every other confidence interval or hypothesis test, there's assumptions and conditions. And just like usual, there's an acronym to help you remember these. For this one, conveniently, it's line. We want to check the scatter plot to make sure that it's linear. That's the L. Okay, we want to make sure the other three of these are all about the residuals. Okay, the residuals must be independent of one another. We can just state that same sentence every time. N is nearly normal. Okay, if we put the residuals into a normal probability plot, we would want to see a plot that's reasonably straight with no outliers. And then the last one is called equal spread. This is just when we look at that residuals plot, we want to see something that's sufficiently scattered with no pattern, no form to it. So when it comes to checking these conditions, we have to do them in a specific order. So first thing we do is we check the straight enough condition. We look at the scatter plot, we make sure it's straight. If it's not straight, we try to re-express it. That's what we did back in chapter 10. If we can't do that, we're just going to stop and end the problem there. Okay, if we can make it straight, or it's straight to begin with, we run the regression. That's what creates the residuals for the problem. After that, we look at the residuals. We make sure there's no pattern. Okay, if that looks okay, then we make a normal probability plot with the residuals. And if that's also okay, then we go ahead and we do our confidence interval or hypothesis test. With every other hypothesis test and confidence interval, when I've done the notes, I've worked through the math of the problem. We're not going to do that with this because it's not important. So we're just going to do this entirely in the calculator right from the start. Okay, so the actual test is, based on our sample of 11 values, is there an association between temperature on race day and the time it takes for this runner to complete the half marathon? Okay, it also gives us an alpha level of 0.01. So basically we have these 11 values. Is that enough for us to conclude that that temperature and the race time are associated and there is a relationship in between them? So those are the values there. We're back to having a P in phantoms, okay? And we would say let beta 0 represent the true slope between the temperature on race day and the time it takes for the runner to complete the race. Our null hypothesis is always that beta 0 equals 0. The true slope equals 0, meaning that there's no association between those two variables. Okay, a slope of 0 would be perfectly flat, meaning it's not positive, it's not negative, they're not associated. Okay, in other words, they're independent. The alternative in this case, it's just that they are associated. Okay, it would either be positive or negative, uphill or downhill. Okay, depending on the wording of the problem, it could be greater than or less than. So it could say, is there a positive association or a negative association? Okay, so just like all our other hypothesis tests, it could be any of those three options. Here we have our four conditions. The scatter plot of race times versus temperature is linear. The residuals are independent of one another. A normal probability plot of the residuals is reasonably straight with no outliers. You have to graph this just like you had to graph all the other nearly normals. And equal spread, the residual plot is sufficiently scattered with no form. Name the test. This is a linear regression t-test. You'll find this in the same list as all your other tests. And when we run it, we'll get a t-score of 4.1634. Degrees of freedom are a little different than usual because this is n-2 instead of n-1 for 9 degrees of freedom. P-value 0.0024, and from here on out, we're familiar. We're going to reject the null hypothesis since the p-value is smaller than the alpha of 0.01. If it gives us an alpha, which it did, we should reference it in this step. There's sufficient evidence to suggest that there's an association between the temperature on race day and the amount of time it will take for the runner to complete the race. That was the hypothesis test. It might also ask us to create a confidence interval, in which case we're estimating the true slope between the temperature on race day, and the amount of time it takes for the runner to complete this race. It gives us an alpha of 1% again, which matches up with a two-tailed hypothesis test. If it was one-tailed, we would want to double that alpha since the alpha is entirely on that one side. P and A we already checked. N, this is a linear regression T interval. Okay, we just run the interval. We get 0.015 to 0.123. And when we write this, we write it kind of like we did when we were interpreting the slope back in Unit 2. So we say something along the lines of, we are 99% confident that for every degree increase in temperature, the mean amount of time it takes for the runner to complete the race will increase between 0.015 minutes and 0.123 minutes. It's an increase because they're both positive. If either were negative, that would indicate it was a decrease.